you ready to go?
I think I'm launched.
Okay. So you
I think I'm live. Hi, everyone. Sorry. Hi, I'm Katerina. I'm part of the ENCODE team. I'll be covering for Nevin today. Today we've got, for this workshop, Moritz Fuller leading the workshop, and the workshop will be on Bitcoin integration and ckBTC. And I will now invite Moritz to take over. Sorry, bear with me. I've sent Moritz the invite.
Hello, guys.
Hello. Yes, we can hear you. I'll let you take over now.
So let me share my screen. I will wait for a couple seconds or minutes. Today we have a very tight schedule, actually. So there's a lot that I'm going to cover. So it could be that we might have maybe 5 or 10 minutes overtime. Just wanted to warn you before we start. So what we are going to do is I'm going to talk about the Bitcoin integration. And then after that, we are going to do a live coding. So I'm going to show you how to use ckBTC for payments in a small example there. And yeah, then we're going to do a quick Q&A. Maybe we do a Q&A after the presentation and another one after the live coding, but it depends a bit on yeah, how fast we are. Okay, I think I'm going to start now. All right. So yeah, hi, my name is Moritz. I'm a developer relations engineer at DFINITY. I've been active in the DFINITY community for more than 5 years, actually. And I'm really happy to give this talk today for the BUIDL Bitcoin Hackathon. And like I already said, this presentation covers the Internet Computer's direct integration with the Bitcoin network. So what actually is the direct Bitcoin integration? In one sentence, the Bitcoin integration allows canisters on the Internet Computer to receive, hold, and send Bitcoin, all directly with transactions on the Bitcoin network. So to understand that this is awesome, we first have to take a look at how things used to work. And a good example, as we are talking about Bitcoin, is ckBTC on Ethereum. So when using ckBTC, you're actually trusting 2 groups of people. The first group are the custodians, they hold the assets, and the second group are the merchants, and they are the only ones allowed to mint or burn ckBTC on Ethereum. And even though the plural of custodian is used, it's actually only one single company that acts as a custodian, and that company's name is BitGo. So to mint ckBTC and thus bridge BTC to Ethereum, a merchant has to send BTC to the custodian, which upon receival means the same amount of ckBTC to the merchant. So if a user wants to bridge his BTC to ckBTC, he has to actually go through KYC and AML with the merchant, send him the BTC, and then wait to receive back the ckBTC. And if a user wants to go the other way around and bridge his ckBTC to BTC, he again has to send his ckBTC to the merchant together with KYC and AML, and then wait to receive back the BTC. And as stated within the ckBTC white paper, you have to trust the custodian not to run away with your funds, not to get hacked, and to honor the one-to-one backing of ckBTC with actual Bitcoin. To minimize the trust, they say the custodian cannot mint tokens on their own, but they need the initiation of a merchant to do so. But it should be fairly easy to find a merchant to collude with to print money out of thin air if they wanted to. They also state in their white paper that their framework minimizes trust, as the credibility of the institutions involved is at stake. And that's not really an argument I personally trust my money with, but I guess that's for everyone to decide for themselves. And we call this type of a bridge a trusted bridge. So a trusted bridge depends on a central entity for operation. It has trust assumptions with respect to the custody of the funds and the security of the bridge. The users rely on the bridge operator's reputations, and they have to give up the control of their assets. So now that we know how things used to work, let's take a look at the Internet computer's direct integration with the Bitcoin network. As mentioned earlier, the Bitcoin integration allows canisters on the Internet computer to receive, hold, and send Bitcoin all directly with transactions on the Bitcoin network. And direct in this context means that no trust assumptions are required other than trust in the correct functioning of the Bitcoin network and the Internet computer. So in other words, there are no additional parties required, such as bridges or other types of intermediaries, resulting in a much cleaner and also more secure integration. And this also means that wrapped Bitcoin from insecure centralized bridge services, which have been hacked for billions of dollars in the past, are no longer needed in DeFi and in Web3. So why is this important? It's important because it opens a lot of new use cases that couldn't have been realized before. A couple, for examples, are on-chain Bitcoin wallets with biometric authentication without the user being required to manage the private key, or social fi applications where users can actually do peer-to-peer Bitcoin transactions using that dApp. You could also trade Bitcoin directly on a decentralized exchange on the Internet computer without requiring any third-party custody of the assets. You could use Bitcoin to buy tokens in a decentralization sale when an SNS-powered DAO decentralizes a service on the IC. An entire class of applications is DeFi, of course, built around Bitcoin, which could previously only be implemented with wrapped Bitcoin that required additional trusted entities. Or chain key Bitcoin, or in short ckBTC, which is an advanced variant of wrapped Bitcoin. And ckBTC is actually probably the easiest way to handle Bitcoin on the IC, and it might be the right choice for many, many developers out there. And we'll talk more about it a bit later. And of course, there are many other use cases that haven't even been imagined yet. So I kind of assume that the audience is familiar with the Bitcoin network, but one thing I want to explain in a bit more detail so that you are actually able to understand the rest of the presentation are UTXOs. So as a simple example here, BTC is used to transfer money. So Alice wants to send, I don't know if you can see my point, 1 second. Yeah, it looks like. So yeah, Alice wants to send 400k Satoshis to Bob. And for that, she has to consume 2 unspent transaction units, or in short, UTXOs, which add up to the 400k Satoshis that she actually wants to send to Bob. So she creates a transaction with the 2 UTXOs that are being consumed as an input, and the new UTXO belonging to Bob produced as an output. And the inputs to this transaction were outputs from previous transactions. So to create a transaction on the Bitcoin network, you have to spend UTXOs. And you can only spend UTXOs you own. So each UTXO has a public key associated with it. And you prove your ownership of a UTXO by creating a signature that's associated with the public key attached to the UTXO. And that signature is that little blue ribbon that actually proves that Alice really owns the UTXOs and that she really wants to spend them and set them to Bob. And those transactions are then collected and put into a block, and the blocks again are chained up and form a blockchain. So with that out of the way, let's talk about why no other blockchain has built this direct integration yet. And it turns out that it's not that easy, and there were 2 technical hurdles that had to be overcome to enable a direct integration of BTC into the IC. The first one is a protocol level integration of the Internet computer with the Bitcoin network. And this means that the replicas, or the physical machines that run the Internet computer protocol, directly communicate with Bitcoin nodes. And the integration allows canisters to fetch balances and UTXOs and send transactions on the Bitcoin network. The second hurdle was the development of a protocol suite for chain key ECDSA signatures, including protocols for threshold ECDSA signing, key generation, public key retrieval, and others. And both of these novelties are now available through the Management Canister API. So let's start with the protocol level integration of the IC with the Bitcoin network. Through this, the Internet computer can obtain Bitcoin blocks directly from the Bitcoin network and process the contained transactions. And this allows for maintaining the full Bitcoin UTXO set on-chain on the IC. So now canisters can run queries against the full Bitcoin UTXO set. And this allows them to know about the held UTXOs and thus also the balance of any Bitcoin address, including their own addresses. The Internet computer can also submit signed transactions for the Bitcoin blockchain. And when it does, the nodes directly transmit the transaction to the Bitcoin network nodes without any need for intermediaries that might censor them. And to make sure that the transactions are actually included in a block, canisters can request current transaction fees. So let's go a level deeper and take a look at how the integration is actually implemented. It consists of two components. The first component is the Bitcoin canister. The Bitcoin canister lives on a Bitcoin activated subnet and is implemented as a completely regular but NNS managed WASM canister. And it's made accessible to other canisters via the management canister, as I mentioned already. The BTC canister holds the on-chain Bitcoin-related state, so the UTXO set, outgoing transactions, and the most recent Bitcoin blocks. Whoops, that was one too early. Outgoing transactions, most recent Bitcoin blocks, and the other component is the Bitcoin adapter, which is down here. And the Bitcoin adapter connects to the nodes of the Bitcoin network, much like completely regular Bitcoin nodes do. So the on-chain UTXO set is managed by the Bitcoin canister and adapter, communicating through the Internet computer's protocol stack. And the process actually starts with the Bitcoin canister requesting successor blocks to the latest block it received from the adapter. And then the adapter on each replica of the subnet obtains the block from the Bitcoin network. And the block making replica for this round provides the requested block to the canister through consensus. And once the BTC canister receives the block, it extracts the UTXOs from the transactions contained in the blocks and then updates the UTXO set it maintains in replicated state. So when a canister wants to send BTC, the transaction has to be submitted to the Bitcoin canister. And in the Bitcoin canister, it is then queued. That's this thing up here. So every subnet round, the Bitcoin adapter on each replica then obtains pending transactions from the Bitcoin canister and queues them for being submitted to the Bitcoin network. And a cool side effect here is that this really leads to an efficient and very quick distribution of transactions in the Bitcoin network, as every replica of the subnet submits the transactions via multiple connected nodes of the Bitcoin network. So now we know how canisters can obtain the UTXOs or the balance for a given Bitcoin address, and also we know how they send transactions. But what's still missing is how they can actually hold BTC and securely sign transactions. And to understand how this works, we have to take a look at the second engineering novelty, a threshold ECDSA protocol suite called chain key ECDSA. In a threshold ECDSA protocol, the private ECDSA key is secret shared between multiple parties, and only an eligible quorum of the parties can generate a signature using their respective private key shares. And that means that the secret signing key is never stored in one location, because otherwise that would become a single point of failure. But instead, it is split up in secret shares, and each secret share is stored on a different machine, so on a different node in the subnet. So to be able to sign a message with the secret key, these machines or nodes or replicas must agree to sign a message and coordinate with one another to generate a signature in a distributed fashion. It's important to mention again, the private key never exists in reconstructed form, but only in its secret shared form, even when signing messages. So with this protocol, each canister can control a vast number of derivable ECDSA keys and obtain signatures for them. So since Bitcoin addresses are tied to ECDSA public keys, this makes it possible for canisters to receive, hold, and transfer Bitcoin directly on the Bitcoin blockchain in a secure manner. So let's take a closer look at the key derivation for ECDSA. So we start off with a master ECDSA key on the ECDSA-enabled subnet generated with the generation protocol. And then from this master key, we can derive canister ECDSA keys. So a single master key is enough to derive ECDSA keys for each canister on the IC using the canister principle as an input. And this key is also called a canister root key. And from canister root keys, again, we can derive an unlimited number of ECDSA keys. So an input to derive a key from a canister root key could, for example, be a user principle. And this way, the canister could, for example, only allow the actual owner of this principle to access the derived key. And that in turn would mean that only the user is able to control that address, allowing them to sign transactions and to receive Bitcoin. And we will see an example of this when taking a look at ckBTC later on. It should probably make a bit more sense then. So now that we have everything we need, let's look at a full transaction flow. So as we know, both the chain key ECDSA and the Bitcoin API are available through the management canister. So the calls that you see here are actually calls to the management canister. So the first step is that we query the Bitcoin canister for the balance of our own address. So that's that thing here. And we derive the address from an ECDSA public key that we retrieve by calling the ECDSA public key method on the management canister, but that's not shown here. So once the result comes back and we made sure that the address actually has enough BTC to fund our transaction, we then request the UTXOs of this address. It's this one here. And the reason is that we, as we learned, we need the UTXOs as an input to our transaction. Another thing we need to do is we have to make sure that our transaction is included in blocks. So we check for the current transaction fee. It's this call here. So now each UTXO that we include in our transaction input needs a signature proving that we actually own the UTXO. So for each UTXO, we call the sign with ECDSA method on the management canister. So these are those calls here. Then we assemble the transaction and finally send the transaction to the Bitcoin network. So because the management canister API that exposes the Bitcoin canister and threshold ECDSA methods is a bit low level, most projects will most likely use chain key BTC. So chain key BTC or ckBTC is a version of Wrapped Bitcoin, like for example, Wrapped BTC on Ethereum, but it has much stronger underlying trust models because of its decentralized architecture and also because it uses threshold ECDSA instead of bridges. So ckBTC is easier to integrate. So instead of using the low-level Bitcoin integration API, you can simply access the ckBTC ledger like any other ICRC1 ledger on the Internet computer. And just for your, so you know, so ICRC1 is basically a token standard on the IC, just like ERC20, for example, on Ethereum. So ckBTC offers faster and cheaper transfers. So ckBTC can be transferred with the low finality time of the Internet computer, so within seconds, and also for a fraction of the costs of a Bitcoin transfer on the Bitcoin network. And using this scheme, only the settlement transfers with the Bitcoin network need to be done on the Bitcoin network. And the majority of transfers can be done with the lightning speed and also the low cost directly offered by the IC. So now that we know what ckBTC is, let's see how it builds on top of the Bitcoin direct integration by looking at the process of converting BTC into ckBTC. So we start by querying the ckBTC minter for a Bitcoin address that is reserved for us on the Bitcoin network. As you can see, maybe just for explanation, to mint ckBTC, you need actually two canisters. So the ckBTC minter, which is the canister that is allowed to create new ckBTCs on the ckBTC ledger, which is the other canister over here. So yeah, we request the address. The address is based on our principal ID and controlled by the ckBTC minter. So now that we have the deposit address, we actually transfer the BTC we want to convert into ckBTC to that address, which is a Bitcoin address, on the Bitcoin network. So this is a transaction on the Bitcoin network. After the transaction is final, we call the update balance method on the minter to notify the minter, triggering it to check for new UTXOs that are associated with our address. This is what the ckBTC minter does then. It will filter the UTXOs by the ones that it has never seen, and then transfers that amount of ckBTC into the account of the user. That happens here. So this way you converted BTC into ckBTC. And to go the other way around, the user sends his ckBTC to a dedicated withdrawal account that is also based on the user's principal and also controlled by the minter. And note that this time, the transfer we make is a call to the ckBTC ledger on the internal computer. And once that transaction is complete, again, we will notify the minter about our transaction by calling the retrieve BTC method. The minter then burns the ckBTC that are now under its control and calls the send transaction method on the Bitcoin canister to send the same amount of BTC on the Bitcoin network to the user. And then we converted ckBTC into BTC. So that's the presentation. If there are urgent questions, I can maybe answer one or two of them. I will check the chat real quick. Hamid Gaha asked, will there be an ICRC2 version for ckBTC? I think so, yes. I'm pretty sure that ICRC1 will be added as an extension to the ckBTC ledger as well. For reference, ICRC1 is basically the ability to have a proof and transfer from, like for ERC20 tokens, for example, in an ICRC1 ledger. So yes, I think that will be added when it's available. All right, so let's head into building. So the goal with this project is to build a dApp that upon payment returns a fortune cookie. And the goal here is to show how to integrate with ckBTC and ICRC1 ledgers in general. Like I already mentioned, ICRC1 is a token standard on the IC, much like ERC20 on Ethereum. And the cool thing about token standards is, and the cool thing about people adhering and using those token standards, is that once you basically know how to integrate a token standard, you are able to integrate all the tokens that follow the standard. So that's pretty neat. Yeah, so the version we are using for this is 0.13, also DFX version 0.13.0. And we start off by creating a new project that we call Fortune Cookie. We are passing the no frontend flag because we don't need a frontend for this example dApp. So now we are CDing into the project, and I'm going to use VS Code because it has great developer tooling support when you build a Motoko. And that's what we're actually using for this example dApp. We are using Motoko. So let's head into the folder that actually holds the basically hello world code. So this is the actor that currently makes up my Fortune Cookie backend. There's a simple query method in here. And the first thing we are going to do is that we are actually going to add a list of Fortune cookies. I prepared this already, so I'm just going to copy paste this. Those are 50 Fortune cookies that I store in an array. So I'm going to minimize this so it's not in the way. All right, and the next thing we're going to do is that we're going to create a method that allows us to get a cookie from the canister. And we're going to call it get cookie. It takes no arguments, and it returns a result. If successful, it will be text. If unsuccessful, it will be text as well. And then in here, we're going to return OK. And we're going to put a little cookie in here. Now we're concatenating the string with one of the cookies, of the fortune cookies in our cookies array. And we are indexing it or accessing that array by using the current replica time. We divide it by 1,000 because otherwise it's not granular enough. And then we are going to take the modulo 50 of that. So yeah, basically with this code here, we just access one of the indices of the array between 0 and 49. So now there's an error because I have to import the result library, also the integer library, and also the time library. All right, so now we're going to start DFX. I'll stop it first because I think I had a copy running. This sometimes takes a little while, so I'm just going to go the quick route. All right, so now we started our local replica. We are going to deploy our fortune cookie, fortune cookie backend, not on the mainnet, but on our local network. And then we are going to, once this installed, we're going to call our getCookie method, and we should receive our fortune cookie. I'm actually going to format this because it looks better like this. So yeah, as you can see, every time we call it, we randomly get one of the fortune cookies. All right. So that's great now, but the goal is to charge customers for the service, because right now, as you can see, everyone can call it and everyone would receive a fortune cookie, but we want to let people pay for that. And the first thing we have to do is that we have to deploy an ICRC1 ledger locally. As I mentioned, ckBTC follows the ICRC1 standard, and ICRC1 is like an ERC20 standard on Ethereum, so it's a token standard. There are other tokens that implement ICRC1, like for example, CHEP token or the SNS1 token, or also the ICP ledger itself. Like I said, once you know how to integrate with ICRC1, you know how to integrate with all of those tokens. And to integrate or to deploy this ICRC1 ledger locally, we're going to follow the steps outlined in the documentation. So there's a guide here. If you go to docs.internetcomputer.org, you head over to guides, then you go to advanced features, ICRC1 token standard, and then deploy a new ICRC1 token. So yes, the first thing we have to do is we have to download the ICRC1 ledger WASM and also the ICRC1 ledger DID file. So the DID is basically the interface specification for that for that canister. And to download them, which is also specified in the guide that I just showed you, we need the commit hash of the last blessed replica version. And that is basically the replica version that was approved by the NNS to be running on the nodes. And you get the last replica version if you head over to the dashboard, so dashboard.internetcomputer.org, then you click on releases, you scroll down, and you see the latest elect replica version. And if you go up here, you can actually copy this thing. So that's what we need. And then there's like a predefined small shell script that we use to download the newest ledger WASM and also the newest DID file. What you have to do is you have to use that blessed replica hash, commit hash, and add it here to the variable. Then it will automatically be filled in here in the placeholders, and yeah, we'll download the files for you. So let's hit enter. Okay, I'm in the wrong folder. Let's head out of the backend folder. So I'm just going to move this in my root folder. All right, so the next thing, now we have the wasn't file, which we can't really see, but that's basically the pre-compiled the pre-compiled version of the ledger canister. So I only get the wasn't. And what I also have is the did file. And what we have to do now, which is a bit unintuitive, I would say, is that we have to create a public version of this did file, which we are going to call icrc1.public.did. And the reason is that in Motoko, we can't include did files with service definitions that take arguments. And if we scroll down here, a service definition is basically this thing here. And this service definition takes an argument. So when you deploy the canister, you have to provide install arguments. But we cannot really include did files that have those arguments. So we have to remove them in the public version of the did. So we're just going to delete this part. Actually, this entire part. And yeah, that's basically it. What we do is we first deploy the ledger with the normal did that contains the arguments. So with this did file here, because we have to specify like a initial distribution of the funds, the token symbol, the name of the token, and so on and so on. So those are the deploy arguments. So we deploy with this did file first, and then we reference the public did before we actually deploy our fortune cookie backend canister. I can imagine that this sounds really confusing now and really weird, but if you don't get it, don't worry. It's just something you have to do if you follow this this flow. Don't question it, just do it. All right, so how do we actually install this wasm file now locally on our local replica? To do that, we modify the dfx.json file that currently has two canisters specified, our backend and our frontend. And we're going to create a new entry for the ckBTC ledger canister. So let me do that real quick. I prepared this already, so I'm just going to copy pasta this. Oops. That was apparently the wrong thing. Let's see. Yeah, that looks better. All right. So, as you might already know, all canisters running on the internet computer are actually wasm files that have been compiled from higher level languages like Rust or Motoko, for example. So the ICRC1 reference implementation was actually written in Rust and was then compiled to a wasm file that we now use to install the canister. And we can actually specify wasm files to be deployed to the IC directly within our dfx.json file. So that's what we're doing right here. We specify a wasm file that we want to deploy, and we also have to specify a candid file that belongs to that wasm file. And what we also have to do now, before I forget it, crucial step, when we implement, if we want to import that ckBTC ledger in our Motoko code, we have to add this dependency field, which thanks to GitHub Copilot was already autofilled. So now we basically say the fortune cookie backend has a dependency, and that dependency is this ckBTC ledger canister that we specified down here. Okay, so if we only need this canister for developing, so the ckBTC canister, I only need this basically locally to mimic the real ckBTC ledger canister on the mainnet. So when I deploy my project, I do not want to actually deploy this canister to the mainnet as well, because I don't need like another ICRC1 ledger. I want to talk to the real ckBTC ledger that is already deployed on the internet computer. So this is what we specify in this remote field here. We basically say when we deploy to mainnet, replace this like maybe locally running ckBTC ledger with this canister ID, and this is the canister ID of the actual ckBTC canister that's deployed on mainnet, and use the following candid file to talk to it. if you're wondering like, hey, how do I know the canister ID of the ckBTC canister, you again head over to the dashboard, you go to Bitcoin all the way to the right, you click on overview, you scroll a little bit down, and then you actually see the ckBTC canisters, so all the canisters that belong to ckBTC. And here you see the canister ID of the ledger, and that's exactly what we added in here. All right, so when you deploy the ckBTC ledger, we have to provide a couple of arguments to it. So those are basically the ledger arguments in the DIT file here. So yeah, just a couple of things like I mentioned, the symbol, the initial supply, who's the controller, who's the minter, and so on and so on. And because it's like a little bit tedious to write this by hand, and we don't want to like rewrite it every time, and if we want to change something, it's like not really easy to do it. We're just going to create a simple package.json, and we're going to write a couple of scripts in the package.json. So the first thing I'm going to do is npm init, and then I head over into my package.json file. There's like this scripts field in here where I can specify scripts that I want to run using npm run and then the name of the script. And we're going to replace that script section with a pre-written script section that I already created. So if you wonder what happens here, we actually set the minting account. If we go to deploy ledger, you can see we get our current DFX identity, assign this to the principal variable. Then here we say deploy the ckBTC ledger with the following arguments. So we set, for example, the minting account to our current developer principal. We set a transfer fee for each transfer on the ledger of 10 units. We specify a token symbol of ckBTC, a token name, token ckBTC, no metadata. We specify initial balances, so we mint 100 ckBTC to our own DFX identity locally. And then there are a couple of other options. So the cool thing now is that if we want to start a fresh replica, deploy the ledger and the fortune cookie canister locally, including swapping from private DIT to public DIT, which otherwise you would need to do manually by hand. The only thing we have to do now is we have to run npm run start, because this takes care of all of it. It starts the replica, it deploys the ledger with the private DITs, and then it deploys the fortune cookie with the public DITs. So let's try this. npm run start. It takes a little while. Okay, successful, nice. So if this works, we should now with our local DFX identity own a 100 ckBTC. So again, I assign my local developer principal to this variable. I make a call to the ckBTC ledger canister to the method ICRC1 balance off. We can find it in the service description. It's right here, ICRC1 balance off. I have to provide an account. So if I scroll up, this is the definition of account. And that's the exact same thing I pass down here. So a record with a field owner, and the balance I'm interested of is my own balance. So I substitute this principal here with the local developer identity. So I hit enter. Now I should receive 100 ckBTC. So ckBTC has basically, I think, like Bitcoin 8 decimals. So if you take like 6 and then another 2, if you take those 8 away, I actually got myself 1,000 ckBTC, not 100. That's how you have to interpret this number down here. It's actually Satoshis, not, or CK sets, not ckBTC, what you receive. Okay, now, cool. I have the ICRC1 ledger or the ckBTC ledger deployed locally. I have some ckBTC that I own or hold with my developer identity, and now I want to import this ckBTC canister into my project. And now it's really easy to embed the canister. So the only thing you have to do is you write import ckBTC ledger, and then there's this special import syntax that you can use where you say canister, and then you just specify the name of the canister that you added to your defx.json. So this ckBTC ledger has to be the same as the name that you gave the canister here. And that's it. Now I can make calls to my ckBTC ledger, both locally when I develop, then it will talk to the ckBTC ledger on my replica locally. But when I deploy to mainnet, it will automatically substitute this ckBTC ledger reference with the real ckBTC canister that's already deployed and live on the mainnet. So that's really cool and really helpful. All right. Now what's left to do is we actually have to write the payment flow logic. And let's go back to the presentation, because this is the payment flow that we are going to use. Some people call it transfer notify, but I don't even know if it has like a real unique name. It's basically based on the same principle as the minting of ckBTC. So the client on the left-hand side first has to ask the receiver, which provides the service. In our case, the receiver is the fortune cookie canister that provides the service of getting a fortune cookie. We have to ask this receiver for an invoice. So in this invoice, we should specify the address that the funds or the account that the funds have to be sent to, and also the amount that we have to send. And the account that I get back in this invoice is based on the calling or the caller principle. So I derive the account based on the principle of the caller. And then, I send this invoice back to the client. The client transfers the amount to this unique account that is based off of its own principle. And then so this is the transfer. And then we call the get cookie, which is the method to get a fortune cookie, as basically our notify. And that way we say like, hey, I paid, now give me a cookie. What the receiver, so the fortune cookie canister does then is it checks the balance of our unique account. It can derive that balance again by just checking the principle of the caller. If the balance is bigger than what has been specified or equal than what has been specified in the invoice, the balance is transferred to the treasury account. So out of the user account and into the treasury account. And once that's successful, we actually provide the service. So we actually send the fortune cookie back to the client. So the first thing we are going to do here is that we're going to create a new file, which is called types.mo, that will hold our new types. And I've already pre-written them. So this type is basically taken from the ICRC1 DIT file. So it's just what the ICRC1 ledger expects when you send it an account. And the other type is our invoice. So the invoice has a to field that is of type account and an amount field that is of type net, so natural number. All right, so now we are going to write the get invoice method that actually returns an account to send the funds to and also the amount to send. And like I said, this is basically the invoice the user has to pay before getting access to the service. And what we do is we access the caller of the method and then derive the account off of that. So because we are short on time, I will copy paste this. And this way, each caller has his own unique sub account to send funds to. Now, I first have to import the invoice type, and now I have to create the create invoice method, the to account method, and another method actually. So again, we are going to create a new file that we call utils.mo, and in this file we are implementing a couple of methods. Again, for the sake of time, I will just copy paste this and explain real quick what we are doing. All right. Yeah, so the first thing we do is we write the to sub account method, and we write the to sub account method in a way that for each principal we can derive a deterministic receiver controlled account to send funds to for paying for our service. And therefore, like I mentioned a couple of times now, but I want to mention it again, therefore we encode the caller's principal as a sub account. So we take a principal, we do some, not some magic, but some, let's say, encoding, and we return a sub account. A sub account is a 32-byte array. I'm not going to go into the details of how this works. If you're interested, you can take a look. This is taken from Research AG. Thank you at this point. All right, then we write the to account method that takes the caller principal and the canister ID. In that case, this will always be the canister ID of our fortune cookie canister. And then it returns an ICRC1 account type. So an ICRC1 account type, we've seen this a couple of times before now, has an owner, which is of type principal. The owner of that account is our canister, so the fortune cookie canister, and then a sub account. And this is now specific to the caller. So the account is controlled or owned by the canister. And for each caller, we send the funds to a specific sub account under the control of the canister. So that's how you have to imagine this. All right. And finally, we write the create invoice method that takes the account and the amount and creates an invoice and sends it back to the caller. All right. Now we head back to main.mo and actually import those methods. So it was create invoice, and what was the other one? To account, and we import this from utils. Okay. Now another import I have to make is this principal. And what happens here is, because to create an invoice, as we know, we have to specify the account. And the account contains a caller field. I know the account takes an argument, a record, which has a caller field and a canister field. And the canister field should be basically the canister ID of our own canister. And to get the canister ID of your own canister, there's a method that is called from actor in the principal base library, and that takes a reference to an actor. And I call that reference fortune cookie, but that reference doesn't exist yet. So now I'm going to call my actor fortune cookie, and that error should disappear, and we are all set. And we actually want to get a 100 sats, which is like, I don't know, 2 or 3 cents for our service. So let's take a look back at the payment flow to see what we achieved. So what we implemented so far is the get invoice method. So the client calls the get invoice method, receives an invoice, and then uses the information contained in the invoice, basically the account to send the funds to and the amount of funds to send, to initiate this ICRC1 transfer to the account. So that's what we have implemented so far. So let's go back to our code. Now we have to somehow modify get cookie in a way that a cookie will only be returned if a payment has been made. So before carrying out the action of sending back a fortune cookie, we have to check if the user actually funded the dedicated account with enough ckBTC. And to do that, we query the ckBTC ledger for the balance of the derived account from the principal, so pretty easy. And we know the signature for the balance method from the ICRC1 specification, and also the compiler would help us to get things right. So I'm just going to copy pasta this again. That's the wrong one. Second. Here we go. So yeah, now it complains because in my to account method, I expect this caller field, and what I have to do is I have to add shared caller, and that way we basically get access to the caller of that method. So when someone calls the get cookie update method on our canister, we now have access to the identity of the caller. And like I said, that's the same basically pattern we use down here to derive a specific account for a caller. All right, so now we have the balance. Next, of course, we have to check whether or not the balance is big enough. So did the user actually send the 100 CK sets? And if not, we return an error saying, hey, not enough funds available in the account. Please make sure that you send at least 100 CK sets. All right, so now if the check has passed and the user actually sent enough ckBTC to the address, we are going to transfer all of the balance of the user sub-account to our treasury sub-account. And for that, we actually have to make sure that we set the correct transfer fee of 10 Satoshis. And we also, because that's the fee that ckBTC expects or that deducts from your transaction. And we have to make sure that we also deduct the fee from the amount that we are transferring. And again, because of a lack of time, I'm going to copy paste this entire block and then go over it and tell you what happens. So the first thing is that the to sub account method is missing. That I'm going to import real quick to sub account. All right. So yeah, like I said, if enough funds were sent, we move the funds to the canister's default account, and that's an ICRC1 transfer on the ckBTC ledger. This is the arguments that the transfer takes. So like I said, we are going to set a transfer fee of 10 CK sets, and we are going to deduct the transfer fee from the balance because otherwise the transfer would fail. Because for example, if the user sends 100 CK sets to the account and I'm trying to transfer 100 CK sets out of the account with a transfer fee of 10, that would be 110 CK sets. And then the transaction would fail with a not enough funds available error. All right, and like I said, we transfer the funds to our treasury account, and the treasury account is actually like the default sub account, which is like the 32-byte array with like 0 bytes. So like the 0-byte account. You can achieve this by just writing null here instead of like creating this 32-byte array. All right. So now we have to make sure that a payment really only triggers the action from the canister once. Because, for example, like I said, the ledger could return an error saying, hey, there are not enough funds available in the address. So we actually have to take a look at the transfer result, because even if I send the transfer, it could still not be successful on the ckBTC ledger. So this is what we do down here. We actually switch over the transfer result, and in the case of an error, in the case of a transfer error, we ourselves return an error saying like, hey, we couldn't transfer the funds to the default account, and we are going to show this transfer error that has been returned by the ckBTC ledger. Another thing that could happen is that there could be an asynchronous error thrown. So maybe the message queue is full or some other unexpected thing that could happen, and that we also have to catch. So in this case, we have this try catch block around the entire operation basically. And if there is an asynchronous error thrown, we're going to catch it, and we are going to return the reject message together with the reject message to the caller. And we can extract this message using the arrow-based library that I also have to import, of course. All right, let's again visit the payment flow to see what we achieved. So this one we did in our previous step, and now we also have this transfer this notify method functionality implemented basically. So now when a user calls get cookie, we actually do check if the balance of the user's unique account is big enough. If so that's happening here to check. And if so, we are transferring the entire amount to our treasury account. So that's also implemented. And if all of this succeeded, then we send the cookie back to the user. All right. So let's redeploy the fortune cookie canister. I'm just going to dfx deploy fortune cookie backend. There should be a warning now because I think okay, yeah, it works. And now we call the dfx canister call fortune cookie backend get cookie. And now this should not work because we didn't send any funds to the sub account, right? So as you can see, we get the error result now with the mention like not enough funds available in the account. This is the error message up here. So what we have to do, we have to call the get invoice method first to get like our unique sub account and also the amount of ckBTC that we have to send. So we do this with this call. Yeah, that's basically telling me where I have to send the funds to and how much I have to send. So using that account, we now send funds on the ckBTC ledger. And luckily, the invoice that is being returned from the get invoice method is the same type as the arguments that ICRC1 transfer takes. So I can easily just copy this part here. I have like a template prepared. So I'm just going to copy that back. So we are making a call to our local ckBTC ledger. We're going to transfer the specified amount in the invoice to the specified account from the invoice. And let's hit enter. Okay, so this looks like it worked. And now we're going to call get cookie again, because now we transferred the funds. So we are basically now, the transfer step is over. Now we're notifying the canister of our transfer. So we're calling get cookie again. The canister checks, it sees the balance was big enough. It transfers the ckBTC to the default account, so to the treasury account, and then it returns our fortune cookie. Call it again. Again, we should receive the error because there are no funds left in the canister, in the sub account. All right, so this is all nice and shiny locally, but let's deploy this on mainnet because this is where the real deal happens. So we are going to use the network IC flag to deploy this on mainnet. And there's going to be a weird error now that I already reported. So we have to create like a new folder. If you encounter this, you go into DFX, IC, canisters, and then you create a folder in here that you call IDL. And then this error should hopefully disappear. All right, so now we do the exact same steps that we did locally, but we are going to do them on mainnet. As you can see, every call I make now has this like -- network IC flag. So now our fortune cookie canister is deployed on the real internet computer, and it's going to communicate with the real ckBTC canister. So if I call get cookie now, because it didn't send any funds anywhere yet, it should basically error out like previously and tell me like, hey, you didn't send enough funds. This takes a little bit longer because it's a inter-canister cross-subnet call. So yeah, we need an invoice. So we are going to call the get invoice method on the canister. That's our invoice now. And because, like I said, we deployed the canister on the mainnet, it will talk to the real ckBTC ledger. And now to pay for our fortune cookie, we actually have to send real ckBTC to this account here specified in the invoice. So if you want to get your hands on ckBTC, what you can do is you can go to iclight.house or icpswap.com. Those are two dApps that offer you the ability to, like I said, either trade ICP for ckBTC or swap ICP for ckBTC or other tokens, or you can also mint ckBTC directly from Bitcoin on those services. So maybe iclight.house, that's the first one, and the other one is icpswap.com. So those two, at least those are the two I'm aware of. There are probably more, but yeah, just if you're interested. Okay, so I did that already. So I already swapped some ICP for ckBTC, and I sent those ckBTC to my developer identity. So now let's transfer the 100 CK sets to the address that is, or to the account that has been specified here. So again, I'm going to use my template and basically just substitute this. That didn't work. Okay, so this is the transfer call on mainnet network IC on the ckBTC ledger, where I transfer the 100 CK sets to the to my dedicated sub account on the fortune cookie canister. All right. So that works. So we already have, this is basically always the block height that you receive. So we already have like around 50K ckBTC transactions. That's pretty cool. So yeah, what we can do is we can basically now, kind of like check whether or not the funds arrived. So we can call the ICRC1 balance off again. Let's fill out this template again, and let's see if this account up here actually holds the 100 CK sets now. And as you can see, it does. You can also check those ckBTC transactions if you go to the dashboard again. So here we have like transactions. You can see all transactions, and this is basically my transaction. This is the 0.000001 ckBTC that I sent. If you compare the block height that has been returned here, that's 48,683, 48,683. So that's my transfer that I made to my dedicated sub account on the fortune cookie canister. All right. So now let's call the get cookie method to actually get our fortune cookie that we paid for, and to actually notify the fortune cookie canister of our transaction. Again, it takes a little while because it has to make a cross subnet call. All right, perfect. That worked. If you call it again now, it shouldn't work. Great, great fortune cookie. By the way, your potential is limitless. Believe in yourself and aim high. I think it's great. All right, as you can see, it does not work. Another thing we can check now is the balance of our treasury account, if the funds actually arrived there. So let's do that. Let me quickly copy the principal of the canister and paste it in my template. All right, so now we call the balance of the treasury of the default sub account or account. And as you can see, it's 90 because we have to pay for the transaction itself. So we only can set 90 CK sets because 10 are reserved as a transaction fee. All right, and again, we could check this transaction on the on the Explorer. So this is the 0. something or the 90 CK sets that have been transferred from my user sub account to the default /treasury sub account of the fortune cookie canister. Okay, so that was a lot, but I think it's pretty cool. You could now potentially build a dApp and yeah, let people pay for services that you offer. This demo dApp is also available on GitHub. So if you are interested in the code, or if you want to follow along, it's this URL that I'm also going to send here in the chat. And yes, that's basically it. I will now check the chat for questions. Okay, so Roger said, would be nice to share some GitHub repo examples on Discord so we can integrate BTC payments into existing projects. Yes, so basically I will share this repository which integrates ckBTC payments in the Discord, in the dedicated Encode Club channel after this talk. Will the recording be available after? I think so, yes. Steve said, need to watch it half speed again to sink in. Sorry if I've been too fast. It's really been a lot of content. It was, I mean, I don't know what time it is now. Yeah, 7 minutes over time. No Q&A. Sorry for that. But it's a very, yeah, it's a complicated topic, I would say. More of an advanced topic, but it's really, really, really cool. Also from like a technological point of view, I think the Bitcoin direct integration is really, really massive. Also it's crazy what the team did there. And also ckBTC is super nice. I can only recommend you to play around with it, mint some ckBTC, send it to your friends. It's really, to me, it was like kind of like mind-boggling that I now like really own BTC, but I have like finality of 2 seconds. I only pay 10 Satoshis and transfer fees, and I can get back to BTC at any time. And there's like no custodian of my funds. There's no hack or something that could happen. So that's like really, really, really cool. Okay, and Gotham asks, is there any implementation example to mint ckBTC from BTC directly? There actually is. It's in our, we have a repository on our GitHub account. It's called examples. And if you go in here, you can pick basically either Motoko or Rust down here. You will find in both folders, you will find a basic Bitcoin example. That's, I don't remember if it's about minting Bitcoin or like minting ckBTC. I think it's more about like this low-level integration that I mentioned in the presentation, where you really send BTC on the Bitcoin network using threshold ECDSA signatures, and also make using the Bitcoin canister to retrieve UTXOs and to send transactions to the network. That this is something that's being handled here, if I'm not mistaken. But regarding minting ckBTC, you could basically really just follow the steps I outlined in the presentation if you want to integrate, or if you want to build a dApp where people can mint ckBTC from Bitcoin or the other way around. So the only thing you really have to do is you have to call like 2 methods. So basically the get BTC address method, and then initiate a transfer on the Bitcoin network, and then call the update balance method, and that's basically it. So it's like super simple, I would say. And yeah, if you want to go the other way around, check this one out. There's also extensive documentation. So again, if you go to docs.internetcomputer.org and you head to guides and then advanced features, and then to Bitcoin integration. Well, actually, let me think. Yeah, so this is more on the low-level side again. I think our wiki is currently down, unfortunately. Oh no, it's back up. Okay. Somewhere are some some descriptions about how to do that. At least, I would guess on the ckBTC. Let me see. I actually have. Wait, going to share this with you guys real quick. Publish to web. Copy wrapping. So at the end of this is basically what I used the text guide to build this example dApp. And at the end of it, you will find like a lot of resources. So those are basically like all the links all the resources that I use to create this presentation and to create the code example. So there's a lot of stuff in there, but if you really want to dive deep into it, you will definitely find some hints here and there. Are there
Great.
any more
Thank you so
questions?
much, Moritz. I think because we've gone a little bit over time, if anyone has any other questions, feel free to put them in the Discord, and we'll make sure to kind of pass them on. But that was super interesting. Thank you so much, and thank you for everyone for staying attentive and asking questions until the end. So yeah, that's all from us. We'll close the session up now, and thank you so much again, Moritz. Bye-bye.
Yeah, thank you guys. Bye-bye.